Hello students, in this video we'll see an example of computing arc length and surface area of revolution of a parametric curve. We're going to consider the parametric curve x of theta is cosine of theta plus theta sine theta, and y of theta is going to be sine theta minus theta cosine theta. This is an example we've worked with a lot. It's the involution of a circle, right? And I'm going to specify that theta is between 0 and 2 pi just for this argument over here. So of course this is our involution of a circle. Found by wrapping a string around the circle, holding the string taut, and then pulling the string away from the circle, right? That's the sort of shape you're going to get. So the involution roughly looks like this. Start over here, right? And then our curve looks basically like that. That's our involution. And what I want to do is I want to first find, so part A of this problem, part A, is to find the arc length. So let's do it. So what's the arc length? So the length of arc is going to be the integral from 0 to pi over 2, because that's the parameterization we're given. And then the square root of what? Then I'm going to put in the square root of dx d theta squared plus dy d theta squared, and then a d theta. Okay, that's our arc length formula. And so what will this be now? So that's our arc length differential. And so what's dx d theta? Well, it's going to be, we've seen this many times before, so let's check right over here as well. It's x prime of theta. It's going to be negative sign, then a positive sign, so now I'm going to get a what? Just a theta cosine theta. And what's our y prime going to be? So I'll have a sine theta, then over here I'm going to have a what? I'm going to have a, when I do the derivative over here of sine, I'm going to have a cosine of theta. Do a theta derivative, I'm going to have a positive cosine. The absolute will vanish, and I'll just do the derivative of cosine, which is sine. So y prime of theta is just going to be theta sine theta. Okay, so we can just fill these in now. Okay, so what will this be? This is going to be the integral from 0 to pi over 2, the square root of theta squared cosine squared of theta, plus theta squared sine squared of theta d theta. Now they both have a common factor of theta squared, so I can pull that theta squared out. So I can pull one theta out. So this is going to be what? This is going to be the integral from 0 to pi over 2 of absolute value theta, because theta squared, pull it out, you get an absolute value theta, which we're going to be able to drop the absolute value since theta is positive in this range. And what's left over is the square root of cosine squared of theta plus sine squared of theta. But we know from the Pythagorean identity that that is just equal to 1. So this is just the integral from 0 to pi over 2 of theta d theta, which is theta squared over 2. So our total, evaluate from what to what? From 0 to pi over 2. So our total length of arc is going to be what? It's going to be pi squared over pi over 2 squared, which is pi squared over 4 over 2. So we get pi squared over 8 is our length of arc of this involution. Part B of this problem is to say rotate this around the x-axis. So I'm going to rotate this around the x-axis. Part B, find the surface area of revolution around the y-axis. Around the x-axis rather, not y-axis. Okay, so what's that formula? That formula is going to be the integral from 0 to pi over 2 of 2 pi times y. Okay, so 2 pi times y. What is y? Y is given over here. Sine theta minus theta cosine theta. Okay, that's my y. And then what? And then times ds, which is this thing over here. So what is ds? We found that ds is just d theta, so I have an extra factor of theta over here. So I have a theta d theta. And so what this simplifies to is this is going to be 2 pi, the integral from 0 to pi over 2. And then what? I'm going to have a theta sine theta, and then a minus theta squared cosine of theta, right? D theta. And then this integral over here can be evaluated by doing a couple integration by parts in a row. So that's a good Calc 2 exercise to sort of go back and do the integration by parts and find out the exact formula for the surface area. But this equation over here, once we integrate it, will give us what the surface area of revolution is around that surface. And the key idea here is that you always have what? 2 pi times y times your ds. And I've dropped the absolute value over here because, again, theta is in the range where theta is not negative. Thank you very much.